So pretty much sometimes they give you all this information, sometimes they don't, but a lot of times, I'm just going to kind of put like a little bracket around this. They might not give you the totals of the columns and rows. Some do, some don't. It's just going to kind of depend. So that might be something that you need to calculate for a question. But on the one that I have here, I do actually have the totals for each of the rows and columns. But it's basically just a relationship between two different sets of variables. So what I have in the table here, this is just kind of the two different variables is whether the student studied or didn't study for this, I don't know, they're just their grade overall, I guess. It doesn't say a test or quiz. And then the other category is whether they passed or failed. You can have more than two, you could have like 3 columns and 2 rows or something. So these could be larger than this, but it just relates to different concepts basically. Now, if you guys are looking at this table, just to read it, can you tell how many people total were surveyed in the table? Like, what's the total number of people? The 30. Total should be, if they don't give it to you, you can complete it yourself, but it should just be in that bottom corner if they give it to you. So this is going to be 30 people. All right, now, can you tell from that table just how many people, let's say, passed the class? How many people, what number in that table is going to tell me how many people passed? Eli, what do you think? 20, 30. All right. How many people failed? 7. All right. How many people do you think spent some time studying? The 20. Okay, you guys, is this making sense? How many people didn't study? 8. Okay, so if you guys can read that. Now, we're going to do our probabilities here. Okay, now, what is the probability? I randomly grab somebody that's been surveyed here. What's the probability that they would have studied? Like, how would you figure out? And you don't have to reduce the fraction or anything. Just tell me, like, what would you do? What over what to figure out the probability I randomly selected somebody that studied here? Exactly. So 22 out of 30. If you want to reduce it, it's 11 over 15. Or if you want to do the decimal, it's totally up to you. Okay, what's the probability I randomly pick somebody and they failed? Randomly going to pick somebody that's been surveyed here. What's the probability they failed the class? Don't everyone volunteer at once. What do we think? Jax, you tell me. All right, 7 out of 30. That doesn't reduce. Just leave it alone. Okay, now, this is kind of interesting. So this says the probability I pick a student, and it's got 2 requirements. It says they studied and they passed. How would I figure that out? The people that studied and passed. Brody, what do you think? 21. Exactly. Or 21 out of how many? You picked the right number on the top. Yes, that's all it is. Okay, so it's 21 out of the whole group. Okay, so basically there's like an intersection here. Like if I just did the people that studied, right? We could do all 22 people that passed, the 23, we could add those together and then we could subtract the overlap. But if it says they studied and they passed, you just have to look for that place. Let me grab a different color highlighter. Just look for that overlap on the table. Those are people that fall into both of those categories. They studied and they passed. So that would be the 21 out of 30, the total number of people. Okay, what about people that passed and did not study? So they passed the class, but they did not study. How many people would that be? What do you think? Say that one more time. Yes, she reduced it for me. Okay, so she says 1 out of 15. If you were looking at the total, it'd be 2 out of 30, which reduces to 1/15. But again, you're looking at the overlap they passed, but they did not study. So it would be just those two people fall into both of those categories on that table out of the total 30. Okay, now this one's a little different because this is an or statement. So an and statement, you're looking for an intersection on the table of those two columns or row and column that fit both the categories. Now, if you're doing an or statement, so let me just do the first one. So it says they did not study or they failed. Okay, if they didn't study, there's 8 people that didn't study, right, out of 30. Or statements, we're always going to add stuff up. They failed, all right? There's 7 people that failed. All right, now, what I would have to do is subtract any overlap. So anybody that did not study and also failed, I counted them twice, which would be in that group 6 people out of the 30, because I counted that in the failed category. I also counted that in the did not study column. So I have to subtract out that extra 6. Now, these guys all have a common denominator, so you don't have to do anything with that. So it should just be, let's see, 15, so 9 out of 30. And if you want to go ahead and reduce that, both of those guys are divisible by 3, so this would be 3/10. So I just have to subtract off the overlap while I'm doing that. All right, see if you guys can figure out what would you put for how many people passed and passed or they studied. So like find the total for each and then see if you can subtract out any overlap that you would have. And I'm just going to do it up here while you guys are thinking about it. And remember, your probability can't be more than 1. So it has to be maximum of 1. That means it has to happen. Okay, so let me pull the table down a little bit here. Okay, so basically, if you are doing an or statement, so for this one, the number of people that passed, that's where I grabbed the 23, and then the number of people that studied, that's where I grabbed the 22. So what happens here? I'm just going to use my highlighter here, maybe. Which color did I not use yet? Okay, so this is the people that passed. And this is the people that studied. Do you see how I counted the 21 twice? Because it's in both of those categories. So that's why I'm going to subtract out the 21. That's a really good question. But you're basically subtracting out the overlap because they're not mutually exclusive. Because you have people who studied and passed at the same time. So that's kind of that concept that we talked about yesterday. So you're going to subtract out that overlap. And so then when I did that, I got 24 over 30, which reduces to 4/5. Really good question. Is anybody else having a question? Okay, so that's just a table. Now I'm going to introduce the concept we're going to kind of work on for the rest of the day, which is called conditional probability. All right, so this says the probability that an event B will occur given that another event A has already occurred. It's going to be a conditional probability, and it only exists, I'm not going to give you guys anything weird where it wouldn't exist in this situation, when events are dependent. This can't work if they're independent events. All right, and the way this is written, it's a little bit weird. You guys will see it kind of down the bottom of the page here. The way you write this is probability, like a P with parentheses. It'll say B, and then it'll be kind of almost like an absolute value bar, like just a vertical line, A, like this. The way you would read that is the probability of B given that A happened. So you know that A happened based on that kind of notation if you see it. So you know that that's the case. And you're going to determine what the probability would be. Okay, now I'm going to give you the technical definition. I totally don't use this. I just use the table and it'll make it easier to work with, but just in case you guys wanted to write it down. Probability of A given B. It's the probability of A and B on the top here over the probability of A. Like I said, I don't typically use that, but it's like the intersection of the two on the top divided by the probability of A. Okay, so how I would read this in a table. What I got in this table down here, this has actually 3 columns. So you have 3 different age groups of people, and then the other part, the rows, are do they ride the bus or not? So that's what we're talking about in this question. So whatever they give you as the second thing. The first one says, find me the probability the person is in the 12 to 13 age range given that they rode the bus. Okay, so here's how I did this. I'm given that they rode the bus, so I don't even look at the other column in the table. So that I'm just given that they rode the bus here, so I know I'm just in that row. So the probability that I am in that age group from 12 to 13, given that I rode the bus. So given that I rode the bus, you're going to put that total on the bottom, because you know you're picking out of this group. You know this person rode the bus. So the probability you grab somebody in the 12 to 13 age range, and then you just go over to that column. So that would be what we would call the intersection. Those are 12 to 13-year-olds that ride the bus, that intersection of the 24. That's what we kind of like on the top. And then A on the bottom would just be the fact that there's 50 out of that group. So then we can reduce this, of course, because both of these guys are divisible by 2. I think this is 12 out of 25. I don't think that reduces any farther. But that's all you have to do. So then if I look under here, conditional probability. Okay, probability they don't ride the bus given that they're in the 16 to 17 age group. So like I wouldn't even look at any of the rest, wouldn't look at any of the rest of the table. So I'm given that I'm in that column, given that I'm in the 16 to 17 age range. What's the probability they don't ride the bus? So then you're just going to grab that intersection, the people that ride the bus in that group, 21 out of 35. That's all you have to do. And I don't think that reduces, but tell me if it does. All right, if you don't ride the bus. Okay, so given that I don't ride the bus, what's the probability I'm in the age group 14 to 15? So don't ride the bus, you're just going to look at that row. Maybe if I can get my marker to sit still. So the probability I fall into the 14 to 15 age range would be the third or the second column there, so there'd be 13 out of 50, and that's all you have to do. And that does not reduce, yes. Of course it does. Thank you. Oh yeah, because they're both divisible by 7. Now I feel like a moron. Thank you. Okay, 13 and 50 don't have anything in common though, so I don't think that reduces. And then I got one more for you guys here. See if you can do this one. So given that you're in the 16 to 17 age range, and I just used my marker to cover up the rest of the question there. What is the probability that I rode the bus? What would you put as your fraction for that last one? Austin, what do you think? Or he's not listening. He's not raising his hand. I thought you were raising your hand. What'd you put for the last one? So if I'm in the age group of 16 to 17. Yep. What'd you say? Perfect. 14, 35. Now go. I know both of those guys are divisible by 7, so I think this reduces to 2/5. Is anybody having a question? And of course, you can use your calculator to reduce the fraction or find the decimal if you need to. Okay. Now, on to the back. This is just another way to display a probability here. And some of these can be kind of tricky and some of them are not too bad. But the top of this is literally just kind of an explanation of what a tree diagram is. And then we're going to work with a couple here on the back. So this is just me stealing information from the internet. So this is a good example, though, of a tree diagram and how it works. So basically you start with 2 things that can happen. So the tree diagram that's up here is like flipping a coin, heads or tails. All right, so you basically start with your event. So I'm going to flip a coin, and they draw what they call a branch. And at the end of the branch, it almost kind of looks like a ray. They write down, okay, this is what happened. So for that first one I just highlighted, at the end of that branch, they flip the coin, they get heads. They write the probability of that happening, usually in a decimal. If you wanted to write a fraction, you could, but they usually write it as a decimal along that branch. And then the other branch, kind of the same thing, probability, if I flipped a coin, I would get tails, also 1/2, and it just points to the different outcome. So the branches are going to represent your probability at the end of it. Like I said, what's the outcome? Okay, and then it says down here, probability of each branch is written on it like that. So this is just flipping a coin twice, all the different possibilities in this tree. So you can keep extending this and making this much larger. So if I flipped a coin, I could get heads, and then if I flipped a coin again, I could get heads or tails. Same thing along this branch. In your first flip, if you get tails, you could, on your second flip, get heads or tails. The way you would calculate the probability is you multiply along the branch. So for example, if I said, what's the probability I got heads twice? You would just multiply 0.5 times 0.5, and then it would give you 0.25, like they have on the, they're just showing you what's the result here. This one would be, I got heads on the first one, tails on the second one, what would the probability be? So that's how the tree branches work there. You just multiply along the branch until you get to the outcome that you want. So we're going to practice kind of filling in one. I kind of started to draw it a little bit here for us. But this says, Doug throws 2 darts at a bullseye. So he's going to throw twice. And it says the probability the first throw hits the bullseye is 0.08. So if you look what I have here, if he throws the dart, he either hits it or misses it. Those are the two options. It says the probability he hits it is 0.08. So I'm going to put that along that branch. Okay. Now, it goes on to say if the first throw hits, so if he hits it on the first throw, the probability the second throw hits the bullseye is 0.04. So this would be my I hit it in my second attempt. Probability I hit it again, it says is 0.04. Okay, if the first throw misses, the probability the second throw hits the bullseye is 0.09. Okay, no, I don't have all this filled in, but based on what this says, it says if the first throw misses, so I would be on this branch, the probability the second throw hits the bullseye, so hit, is 0.09. So let's go back real quick and see if we can fill in the probabilities that we don't have labeled on the branches. So if the probability I hit on the first try is 0.08, what would the probability I miss be? Yeah. Close. She says 0.02. She's a little bit, you're on the right track. Like, what would they add up to? 0.92. This is like 1 and 1 is what they would add up to. So like an 8% chance, then it's a 92% chance I wouldn't hit it. Does that make sense? So along the branch, they have to add up to 1. Or like the 2 branches together, these have to add up to 1. These 2 branches would have to add up to 1. These 2 branches would have to add up to 1. So on this branch here across the top, if I hit 0.04, what would the miss be on that one? 0.96. Yeah, just it has to add up to 1. All right, so like this would be like if I have a 9%, then this one has to be 91%, so add up to 100 if you want to think about it like that. So those are all my probabilities. Okay, now here's how you calculate this. You're just going to go along the branch. It's not hard, I promise. This says the probability you hit the bullseye on both throws. Okay, so hit the bullseye on both throws. You're just going to go along the branches that represent that. So the probability I hit the first time would be 0.08, and then hit again would be the 0.04. And you're just going to multiply those together to get your probability that both of those things happen. And this is pretty small. This is 0.0032. So if I scooch that decimal point over 2 spots to think about that as a percentage, it's like a 0.32%. It's a really small percentage. Now, the question I have next is a little bit weird. So this says the probability we hit the bullseye exactly once in both throws. So if you guys remember, I should probably put this. Exactly is a fancy word that can be interchanged with the word only. Is there more than one way this could happen? If I hit the bullseye once in both throws, is there more than one way that can happen? Okay, if you guys look at this, like, let's say if I only hit it once, right? If I hit it here, but I don't hit it here, that's me hitting it once. So that's one way across that bridge. If I miss on the first, but hit on the second, I still hit the bullseye only once. So there's 2 ways that that could happen. So what I would tell you to do, one way that that could happen, I would go hit and then miss. And the other way that could happen, let me grab a different color, is that I could miss and then hit. Both of those scenarios have me hitting the bullseye only one time. So what you would do, we're going to multiply along the branches here. So the first one, if I hit on the first, that's the 0.08, but miss on the second. That would be to multiply that by the 0.96. That's one way that could happen. Then what I would actually do with that, I would add that to the other probability, the other option. So the other option would be I missed the first but hit on the second. And we can just take and add these guys together, and that would give me the total probability that I would hit only once. So I'd do the 0.08, 0.96, and then I'm going to add that to 0.92 times 0.09. You can do that separate in your calculator, or you could type it all at once. It's totally up to you. But overall, the probability that you hit exactly once, I'll just go ahead and write all 4 of those decimal places because that's what I had there, would be close to 16% that would happen, that you would hit the bullseye one time. And then the last one's actually a conditional probability. So this says, what's the probability you miss given that you know the first throw was a hit? This is a little bit weird, but you don't actually have to do much work with this. What is the probability you're going to miss given that you know the first throw was a hit? You don't have to calculate everything here. You're just going to find it along the branch. So what's the probability I'm going to miss if I know that I hit on the first throw? What do you think? Oh, wow, and I thought you were answering. I thought you had your hand up. Okay. What do you think? Exactly. How'd you get that? I'm just following it, yeah. If you miss, like you know you've already passed this point, you missed, so the probability that, given that you know that you missed, the probability the first throw was a hit is going to be the 0.96. Okay. Is anybody having a question? All right, now the one at the bottom, I'm going to have us draw a little tree here. Okay. So this is a little bit more involved because we don't have any branches to go from. So this says the school system recorded the information below, which we're going to draw because I took it out so we could practice it, from a survey it sent to people who were juniors in high school 10 years ago. Okay, it says 85% of the students graduated from high school. So I'm going to make my first branch, and we're either going to say they graduated or they didn't graduate. And then it says, right in that direction there, it says 85% of the students graduated from high school. Okay, so I'm going to go ahead and put a 0.85 along the graduated line. What would you put along the line for they didn't graduate? If 85% graduated, how many didn't? What percent? 15, right? They got to add up to 1. So just take 1 minus 0.85, or you could just think about like 100 minus 85, so you'd have 15 left. Okay, now, of the students who graduated, so I'm going to be up on this branch here, it says, let's see, 90% are happy with their present job. So I'm just going to write happy. I'm not going to write with their job. And then the other group would not be happy with their job. So it says there 90% are happy with their job. So I'm going to put 0.9 or 0.90, however you want to write it. So how many people would not be happy with their job in that group? 10, right? 10%, so just put 0.10. 0.1, 0.10. Okay, then it says, of the students who didn't graduate, so now I'm on this branch down here, 60% are happy with their current job. And then, so if 60% are not happy, or are happy with their job, what percent would not be happy with their job? 40, right. Okay, so this would be 0.60, this would be 0.40. Okay, so we're just going to do a couple practice probabilities down here after we drew the tree. So it says probability they graduated and they are happy with their job. So we would just go right along the branch. So graduated, 85%, and they're happy with the job. So we would do the 0.85, just multiply along the tree, times the 0.9. And that would be our result there. If I can do it real quick. And you guys can do it on your calculator too. But I'll just go ahead and write out the whole 0.765 there. So about close to 77%. This guy says probability they didn't graduate, so I'm on this branch, and they're happy with their job, so just follow along there. That's all you're going to do. So they didn't graduate is 15% or 0.15, and then they are happy with their job, that's 60%, so times the 0.6. We're just going to multiply those guys together. All right, so I got here 0.09, so that's about 0.9% of the people. This one's a little bit weird. This one says, for letter C, the probability that you're happy with your job. If you guys look at the tree, there's two different ways that could happen. There's the people up here that graduated that are happy with their job, but there's also the people down here that didn't graduate that are also happy with their job. So we want to put both of those branches as options, and we're just going to add them together. Now, if you guys notice, we just did like both of these branches for this part. So the probability that they're happy with their job and they graduated would be this group. So the 0.85 times the 0.9. And the probability they didn't graduate, also happy with their job. We already did that right here. That 0.15 times the 0.6. There's just two different ways that can happen along with the branch. It just says probability the person's happy. So since that has two different endings there, we have two different probabilities. And then we would just add these guys together. So we'd have the 0.765 plus the 0.09 there, which would give us a total probability. Most of the people then, if you think about that as a percentage, it'd be like almost 86% of these people are happy with their job. And then the last one, I always think these can be a little bit easier if you have a conditional probability with a little tree. The probability the person is happy given that you know they didn't graduate. What's the probability the person's going to be happy with their job given that you know they didn't graduate? Don't have to calculate anything here. You just have to find it on the branch. What percentage of people do you think here? Given they didn't graduate, what's the probability they're happy with their job? It's the 0.6, right? All you got to do, you know they didn't graduate, so you know you're not even look at this part of the tree. Probability they're happy is 60%. So 0.6 or 60%. All right. Does anybody have any questions?